Jeffrey is sitting in San Francisco, California, and he sent us a highly specific request. He wants to know what it would take to leave the Bay Area behind and mount a full-scale expedition to either the Earth's North Pole or the Moon's. Right now, Jeffrey is likely enjoying a comfortable 65-degree afternoon. To help him make this choice, we need to pull him out of that temperate comfort zone and drop him into environments that actively reject human biology. This animated globe shows a thermal gradient of the Earth. Look at the top of the axis, where those warm orange bands completely disappear. North, in this context, is a harsh thermal border, where the physical rules change entirely. To figure out which ticket Jeffrey should book, we need to simulate the exact physical forces he will face in both locations, and look at how he will engineer his body and his gear to survive them. He has to decide which set of extreme physical laws he wants to fight against. At Earth's geographic North Pole, Jeffrey will be floating on a dynamic, cracking sheet of sea ice that drifts continuously over a freezing ocean. Getting there requires displacing massive amounts of that ice. You need thousands of tons of steel and raw nuclear power just to break a path through the frozen surface layer. The early explorers who mapped this region relied on rudimentary gear, massive caloric intake, and raw physical endurance to withstand ambient temperatures that regularly drop to 40 below zero. And the cold is only the baseline threat. You are sharing this fractured ice sheet with 1,000-pound apex predators perfectly adapted to hunt in this specific biome. This diagram illustrates a 24-hour cycle at the pole during summer. The sun icon never drops below the horizon line. Enduring weeks of continuous sunlight, or months of pitch-black winter, causes severe circadian disruption, wrecking your sleep cycles and hormone production. You are pushed to the absolute edge of biological tolerance here. However, you still have the distinct luxury of breathing atmospheric oxygen and walking in normal gravity. Launching Jeffrey 238,000 miles upward drops him at the rim of Peary Crater. The terrain here is entirely alien, carved out by billions of years of meteorite impacts. This topological render shows the area's unique astrophysics. Because the Moon has almost no axial tilt, the Sun sits at a permanent 1-degree angle above the horizon. It never rises overhead, casting infinite pitch-black shadows deep into the craters. There is no air here. To step into this hard vacuum, Jeffrey's entire environment must be contained within his suit. He is wearing a highly pressurized, miniaturized spacecraft that regulates his oxygen, scrubs his carbon dioxide, and manages his internal humidity. Without an atmospheric shield, he is constantly bombarded by lethal cosmic radiation. That heavy gold-plated visor specifically filters out the intense solar rays that would otherwise blind him instantly. Without an atmosphere to distribute heat, the thermal regolith hits extreme highs of 250 degrees Fahrenheit in direct sunlight and immediately plunges to nearly 400 degrees below zero the second he steps into the shade. In this vacuum, biological stamina is useless. If a single seal breaks or a cooling tube clogs, the human body fails in seconds. The expedition relies strictly on zero-fail engineering. Conquering the Earth's frozen oceans was a massive test of human grit from a previous century. Reaching the lunar poles is a strict requirement for our immediate future in space. The reason space agencies are racing to the Moon lies entirely within those permanent, freezing shadows. Hidden inside the dark crater floors are massive deposits of ancient crystalline structures mixed directly into the dirt. This volumetric model shows what's beneath the surface. Trapped deep inside these craters are billions of tons of frozen water. Break those water molecules apart, and you get hydrogen and oxygen. You are mining the chemical ingredients needed to synthesize rocket fuel off-world. Jeffrey's personal dream aligns exactly with our current space strategy. Securing these chemical resources allows us to launch heavier payloads, leave our orbit entirely, and establish a permanent human footprint deep in the solar system.